So welcome everybody. Today we have zlem with us from Gazi University in Ankara, we just learned. And she will talk about pseudo-supersymmetric approaches to the Dirac field in different geometries. So whenever you're ready, please go ahead, zlem.
Oh, thank you so much. I want to thank organizers and to all participants, and I'm very happy to be with you all here. And in fact, even the title is different geometries and the abstract with containing the Robertson-Walker spacetimes. The ingredients of this presentation change a little bit because my calculations are in still progress. Some part of this presentation was published before, and some part of this presentation is still being prepared in order to publish. Now, instead of the previous space-time, I want to replace with the open Friedman model. Especially, I want to start with the hermiticity in the curved spacetime in the presence of the time-changing gravitational field based on Parker product. And I want to continue with eta representation in terms of metric components using the Parker product and its equivalence in the pseudo-Hermitian theories, and I want to continue with pseudo-supersymmetry, especially 3 examples, and using the intertwining relationships between the Hamiltonians. I want to introduce the partner operator of the initial operator given in the curved spacetime. For each model, De Sitter, Schwarzschild, and open Friedman models. Then I want to continue with the solutions, exact solutions of the De Sitter spacetime for the Dirac operator. And final topic is into supersymmetry. And this is also containing this QNMF, means quasi-normal mode frequency. This is done for Schwarzschild spacetime. The quasi-normal modes describe, in fact, a long period of damped proper oscillations of gravitational waves. So they are used to detect the gravitational waves, and they are also corresponding to the eigenvalues, the complex eigenvalues around the black hole in general relativity, and also in the quantum mechanics and quantum gravity also. Yes. So by the way, I just forgot to mention that the supersymmetry is it has been connected to quasi-normal mode frequencies, considering the bosonic these quasi-normal modes. By the way, there are 0 modes of a fermionic system. This is also related to the unbroken supersymmetry. So if I start with the works by Parker in 80s, he showed that the scalar product in the curved spacetime was given by this integral. But before, one can see that there is a tetrad basis. There is a set of n independent vector fields, and they span the n-dimensional tangent bundle at each point of the space-time manifold. And there is also a corresponding dual co-tetrads. The other name of the tetrads vectors are known as the Fellbines. So this G is corresponding to the metric tensor. They can be expressed in terms of the tetrads, as they are shown in here. So eta AB is corresponding to the metric tensor in the flat spacetime. So corresponding these underlined gamma matrices are represented by this underlined gamma mu x's space-dependent gamma matrices, and the anti-commutation is equal to the 2 times the metric tensor G mu, and the covariant derivative of these matrices is equal to 0. So this space-dependent gamma matrices is linked to the flat gamma matrices by these tetrad fields. So if you look at the general covariant Dirac equation, this is represented by the equation 1. So this covariant derivative operator is given in terms of this partial derivative operator and the spin connection term. Here, the scalar product is given by this integral. The inside of the square root, there is the determinant of the metric tensor. It can be shown by this. Of course, the time derivative of this this parenthesis is equal to 0. The scalar product time derivative is 0. By the way, the mu nu, these Greek letters are being used for global general space-time coordinates, while we are using A, B, these are used for the Lorentz or local space-time coordinates.
We have a question.
Yeah.
Philip?
Yes, just go back one slide, please.
Yes.
The scalar product, you presumably you've missed a psi on the right, but my real question is, the minus G is the 4-dimensional G, not the 3-dimensional.
Yes. Yes.
And even then, you're saying that the quantity phi psi is time independent.
Oh, yes, phi and psi. No, it shouldn't be. So it's.
Oh, it's not time independent. Okay.
No,
Well, that's fine.
Sure. Yes. If we continue with this Schrodinger's like equation involving this Hamiltonian operator in the curved spacetime, this operator is given by equation 3. In fact, this Hamiltonian can be obtained from the previous Dirac equation in 1. If you multiply this equation on the left by gamma 0, and if you divide it by G00, the time component of the metric tensor, so you can get this Hamiltonian operator in 3. So if you want to perform this difference, because you want to show the hermiticity, so this should be equal to 0. But if the metric tensor explicitly depending on time, then there is such a result. This integral, the difference is equal to that integral. Of course, you can check the parentheses. Inside the parentheses, we have Hamiltonian operators appearing on the right and on the left, right here. In fact, it's a paradox because of the wave function itself, because there is a time dependency in here. When we look at the psi x, the wave function, when the square root of negative g depends on time, so does the wave function. In fact, it can be shown by x cat by this vector sign, so it is xt. So if the complete basis of this xt cat, it satisfies this integral equation. So we can consider that this Hamiltonian operator in 3 is not quite the Hamiltonian operator in equation 2 on the right-hand side. So at that point, one can check the matrix elements if we perform this derivative, time derivative of the cat and bra representations. So this matrix elements can be equal, it can be seen in terms of the inverse of the square negative g and the Dirac delta function, and this is the Hamiltonian operator right here. So you can check that this operator satisfying the condition is given by that relationship. In the pseudo-hermiticity, there is an equivalent representation considering the difference between these two Hamiltonian and Hamiltonian hats. If you look at it, if you consider the same operator, if we begin with the same operator of H, which is given in here, and if we consider the Parker-Waite operator, which is shown by this rho. Rho is the invertible operator, so it is given in the famous pseudo-hermiticity formula expression. Of course, in the standard quantum mechanics, this delta is equal to 0 in pseudo-hermiticity. So this rho can be written in terms of the eta operator. The uniqueness and self-conjugacy of this Hamiltonian system was discussed in Gorbatenko and Neznamov paper. Especially the authors studied the Schwinger's gauge in order to obtain the eta in terms of the metric tensor components, the determinant of the metric tensor and the time component of the metric tensor. This is the identity operator. So you can also use the Lorentz transformation matrices in order to link the space-dependent gamma matrices to the another gamma matrices. Of course, we need Schwinger's gauge because we want to obtain the self conjugacy in the Hamiltonian operator. Now, if we remember the initial Hamiltonian, according to the calculations done by Gorbatenko and Neznamov, they obtained the eta representation of this Hamiltonian. Of course, the metric tensor is varying with time. Now, I want to continue with this pseudo-supersymmetry, this content. In this content, I want to talk about, I want to remind the intertwining operator and the nonlinear pseudo-supersymmetry. This H can be a non-Hermitian Hamiltonian. It can be factorized in terms of A and B. These are general, of course, the first order differential operators. But of course, the factorization of this Hamiltonian in the curved space-time is not working here. So this is, of course, valid for standard conventional quantum mechanics. So we have the partner Hamiltonian operator, which is shown by H subscript S, and the adjoint of this H subscript Hamiltonian, and there is such intertwining relationship between those Hamiltonians. This partner Hamiltonian is known as, it is called as eta2 pseudo-Hermitian. So one can, of course, relate the initial Hamiltonian to the partner Hamiltonian using the other eta operator, which is known as eta 1. So one can, of course, find a relationship between this eta used previously. Eta equals to eta 2 times eta 1. So these are very well known pseudo-supersymmetry and the aspects of this pseudo-supersymmetry.
But I have a question. Your previous Hamiltonian was not pseudo-Hermitian.
Oh, yes.
It was not pseudo-Hermitian, right? The one you showed previously was not.
Yes.
Yeah.
Yes.
Okay. And
No.
the uniqueness you discussed, it was achieved by choosing a gauge, or how does it become unique?
Yes, it is Schwinger's gauge. But by the way, in fact, the H eta, maybe I can show. Yes, this H eta, which is given here, in fact, this is independent from the choice of the tetrad vectors, in fact. There is such a property.
Philip, do you still have a question, or is this an old hand?
No. I have a new question.
Okay.
Why are you using the term supersymmetry? Are there, I mean, do you have Grassmann operators here?
Well, in fact, I'm using pseudo-supersymmetry because of the eta representation and these intertwining relationships. In fact, it is not related to the Grassmann variables.
Yeah, so why are you calling it supersymmetry? I mean, I don't object to what you're doing. I was just curious to know why it would be.
Yes. I want to, my main goal is to find the partner Hamiltonian of the initial Hamiltonian in the curved space-time. So because the initial Hamiltonian operator is here, and this is its Hermitian equivalence, then I want to find the partner Hamiltonian operator of this Hamiltonian operator, the initial Hamiltonian operator. So maybe I can call this Hamiltonian operator by H plus. So previously it was called by HS right here. So H is the initial, HS is the partner Hamiltonian operator. So if I continue from here,
if I can just interrupt you, I'm sorry. You can call HS the partner, but you can't call it the superpartner.
It's the quantum mechanical analog of supersymmetry, Philip. It's a Darboux transformation, and in that context is very often called supersymmetry. It's not it's not the usual supersymmetry. It's the analog in quantum mechanics.
Yes, in fact, it is not the supersymmetry in space-time.
Okay.
Because the Poincare algebra is in 4 dimensions. Okay. So this is not the same, of course. Yeah, so I want to call this initial Hamiltonian operator using H minus in my calculations, H minus, and my aim is to find the partner operator, which is H plus in here. So if I continue with the de Sitter spacetime as an example, L is corresponding to the radius of the universe in this metric. So one can give the total Hamiltonian operator, which is shown by here. Of course, in this operator, the A1 is in fact the vector potential. There is electromagnetic fields in here. So this is my H negative, and one can find the adjoint of this H negative operator using convenience intertwining relations. So, of course, using Gorbatenko and Neznamov methods, we can see that the eta 2 can be given in terms of these components of the metric in this form. So, in the next, because I want to find H plus, the partner Hamiltonian operator, the partner operator, the partner of H minus, I have to find another intertwining operator, which can be eta 1. So eta 1 is not known yet. So this is an ansatz for the eta 1. This ansatz given by me. So if I use these intertwining relationships, I can obtain the partner Hamiltonian operator in the curved spacetime. So eta 1 can be also obtained with this relationship, because in my suggestion, this eta 1 was containing the elements, which is the square of the sine hyperbolic phi, and the power is a3, because it is containing this phi, angle phi elements. The eta 1 is also obtained in this way. Inside of it, you can find the square of sine phi. So there is a question. So I don't know the answer of this question, if it does make sense or not. The question is, if I find eta 1 using the intertwining relationships, then can I call these two metric tensors as partner metric tensors? In fact, this is because of the main question. The main question in my mind was, is there a connection between supersymmetric quantum mechanical algebra and global spacetime supersymmetry? But of course, I know that the answer is no, because as we mentioned before, the dimension, the Poincare algebra in the spacetime is 4-dimensional, but in here, quantum mechanical supersymmetry is given in 1 dimension. But in this way, the G1 mu metric tensor, which is linked to the H plus, is obtained with this matrix. Now, if I continue with Schwarzschild spacetime, and if I repeat the same calculations, one can also introduce the eta again. In fact, this is corresponding to eta 2 in this pseudo-supersymmetric contents. So this is the initial Hamiltonian operator, and this is the Hermitian equivalent of this Hamiltonian operator. So if you look at the time components and the rest of the metric, there is such a function. And of course, the geometric units are used in here. This 1 negative 2m over r is because of that. So the question is the same. What is partner Hamiltonian operator, partner of that initial Schwarzschild Dirac operator? So again, I turn back to the same algebraic calculations. And then finally, I got results, of course. During this intertwining relations, we are using eta 1 related intertwining relationship and eta intertwining relationship. So between these two relationships, we can see that there should be a difference between them, considering the H plus, because if you multiply this equation on the left by eta 1, and if you multiply this equation on the right hand side, this is given, on the right by eta inverse of eta, on the right by inverse of the eta operator, in each case you will get H plus. Then if you take the difference of these two relationships, you should get 0. So from this relationship, I got these equations, differential equations. There are derivatives with respect to space R and the angles inside of this differential equations. In fact, they are the coefficients of gamma 0, gamma 1, gamma 0, gamma 2, and gamma 0, gamma 3 parentheses. So they should be equal to 0. So in the solution, one can arrive at the total eta operator. So this total eta operator, if you remember, it was given in terms of eta 2 times eta 1. So eta 2 is already known. So one can obtain eta 1. So here the j is corresponding to 1 over 4. It can be found as 1 over 4. So this can give us a chance to find the partner Hamiltonian operator H plus, as it is shown in here. Again, from here, maybe one can arrive at the metric tensor, which is linked to the H plus Hamiltonian operator in this form. By the way, I was curious to the expansion of the Schwarzschild metric to n dimensions. And when I look at the literature, there is such a study. So the expansion of this Schwarzschild metric to n dimensions can be given by this formula. So maybe one can, of course, expand this unknown, this function can be maybe r squared times sine phi squared. So we can again, of course, repeat the same kind of calculations for open Friedman model. So there is such a time dependency through this non-stationary metric. So if I continue, so I can also obtain this H plus, of course. So I couldn't continue with my calculations more on open Friedman models because I am now interested in the calculations of Schwarzschild spacetime and quasi-normal modes and the frequencies of both the initial Hamiltonian and the partner Hamiltonian. Now I want to continue with the De Sitter spacetime and the exact solutions. So here it is, this initial equation, initial Hamiltonian operator. So one can, of course, reduce this operator in curved spacetime into the flat spacetime. So we can also separate the time and angle related parts. So, by the way, I can propose this wave function in terms of this separation of variables can be used in here. So this function is used as the vector potential in the previous literature. So the frequency can be taken as omega in here. When we look at the solutions, the angular part looks like a trigonometric partial Taylor-like potential. So we can arrive at the solutions which are very well known in the literature. By the way, of course, the solutions are given in terms of Jacobi polynomials. And when it comes to the time dependent parts, we can look at the time dependency of this insight. There is a kind of complex Eckart-like potential form that there should be a kind of complex Eckart potential, but of course with a wrong sign. There is such a negative sign here. So we can arrive at the solutions again in terms of Romanovsky polynomials. By the way, we can express the quantum numbers in terms of the potential parameters in here. Actually, in the N2 supersymmetry, now I'm focused in this topic right now. It's still continue. The supersymmetry N2 supersymmetry, there is such a hidden supersymmetry considering the Dirac fermion systems around various types of black holes, and there's unbroken hidden supersymmetry. So that's why I'm interested in this N2 supersymmetry. Of course, we can start with the charge operators, and this is a total Hamiltonian operator, factorized in terms of the operator of L. And this supercharged operators, anti-commutation of them is giving us the Hamiltonian operator. The square of these supercharges are equal to 0. And there is a Witten parity operator. It's given by that matrix. So the total Hilbert space composed of the, of course, there are subspaces H plus and H negative. These, considering the vectors of the spaces, are classified to even and odd parity states according to the Witten parity. So partner Hamiltonians can be, of course, expressed in terms of these operators. All right. So there is such a parity operator exerted on the states. And there are also zero modes are defined by the Witten index. In fact, in my calculations, I am, on the other hand, I am focused on these zero modes. Maybe one can find a unbroken SUSY case through the solutions. Now, if I pull the numbers of the zero modes by that number of n plus negative, the difference between them is delta. It is known as the Witten index. So if it is the non-zero integer, then the supersymmetry is known as unbroken. And if when the Witten index is non-zero integer, the supersymmetry is unbroken. And on the other hand, if they are equal to each other, it is broken. And if they are equal to 0, of course, it is broken. And in this case, supersymmetry is not broken, as we remember. Now, if I turn back to Schwarzschild's Hamiltonian operator, I can use the N2 supersymmetry, and I can express the Hamiltonian operator. But of course, this is the radial part of the initial Hamiltonian operator for the Schwarzschild spacetime. And these are, of course, our states. So this Hamiltonian operator acts on those states, fermionic states. And this is adjoint of my Hamiltonian operator. Now, if I apply this transformation for the solutions, wave functions, I will get the parentheses below. And I can, of course, introduce a suggestion for these new solutions of phi. I can separate the time-dependent parts and the space and angular parts using this. And for the total angular momentum, if it is L plus half, I have this vector, I mean the eigenvector, including the angles, and with the coefficients of ALM and BLM. In fact, this reminds us the Dirac equation and solutions of the Dirac equation for central potential in the flat space-time, these ingredients. So now I'm looking at the radial part of this Dirac equation. So if I apply another transformation like R star, so if I use it, my system given previously in here, it becomes this equation. There is such a kappa constant. It's an angular momentum number, and it is defined negative and positive j plus half. So here I want to, of course, obtain a Schrödinger's-like equation. So I have to apply another transformation using this matrix. So if I consider one component F plus and G plus components, and here in my matrix, rotational matrix, this angle theta tilde is arctangent function. If I use these transformations, this total equation becoming the equation below, which is shaded and shown in here. So after that, if I, of course, after using this straightforward algebra, I will get a Schrödinger's-like equation. Right here, these V1 and V2 potentials are like supersymmetric partner potentials. And there is a superpotential, WR, so one can use this superpotential to obtain V1 and 2. The form of the superpotential can be obtained by this function. So this M is corresponding to the mass in here. So I can, of course, draw this potential because it is a huge, yes, I want to show this potential function in the next slides. It is corresponding to that function. It's very huge. And I just try to draw the potential versus R coordinates in order to understand the behavior of this potential. When the M is increased, the I think the peak of the potential is also increasing. For the if you look at the small values of this mass, it can be given in the form of a potential barrier. So in here for the partner Hamiltonian, I try to repeat all these calculations. So there were some extra terms in my results. So they can be, of course, expressed in terms of my previous parameters of A and B that I used before. So again, I try to see the behavior of the potential function. There are some differences between, of course, in the previous potential function. So as the thing is, if the mass increase, the peak of the potential is also increasing. So if the R goes to infinity, so the potential should be approaching to the mass square. So the height of the my potential peak is lower than the asymptotic value. So when I look at my calculations, I couldn't obtain the quasi-normal frequencies at that point. So I'm still trying to understand the behavior of the both potential and quasi-normal modes. In the literature, if you want to calculate this quasi-normal modes, you can look at the WKB approach, which is used in the literature frequently. There is such a relationship. So one can expand the R maximum into a perturbation series. So this is the for the angular momentum parameter, and this number of n given in this formula. And for the mass, I have obtained such a complex frequency. By the way, as I told you, I'm still trying to understand what's going on in this region. So it is taking too much time, of course. So when I look at my studies related to this topic, I was trying to find a link between supersymmetric quantum mechanical approaches and their correspondence in the global space-time and supersymmetry, but it is too difficult, and obviously there is no such representation. So when I also look at my calculations, this Witten index using these operators, which I mentioned before, this Witten index can be found as 0. So this is corresponding to unbroken SUSY algebra for the radial Dirac operator, considering the Schwarzschild spacetime. On the other hand, in this numerical calculations, the real parts of the frequencies are increasing with the angular momentum quantum number, but I still I haven't understood the behavior of the complex parts yet, and the oscillation frequency is increasing with the mass of the Dirac fields. So the energy of this Dirac fields is always higher than the mass term, of course, the m square, as you know. Okay, so that's the end of my presentation. So this study related to this Schwarzschild spacetime and pseudo-supersymmetry and finding the quasi-normal modes and frequencies in this study is taking too much time of me. So that's why I just try to introduce you a small part of this study. After finishing it, I will send this work for publication to a journal. So thank you for listening to me.
Thank you very much. Any questions, any comments?
Thank you.
Yeah, I have a short question. Very early on in your talk,
Yes.
you calculated psi h phi minus phi h psi, and you found that it wasn't zero.
Can I turn back?
Yes, go all the way back, right at the beginning. Way at the beginning.
Oh, yes. Very
Even
big.
more. Even more.
And
Yeah, even more. Okay, that was it. That
Yeah.
page. Now go down. Now go down one more. Now go forward one page. Sorry.
oh, yes, forward. Okay.
Okay. Now on the right, you've calculated phi h psi minus h phi psi. Now, have you thought about the possibility that the ket, that the bra may not be the conjugate of the ket? And would that possibly lead you to something for which that quantity on the left is zero?
Yes, yes.
Instead of you started to look at changing H, but suppose you change the definition of what you call, suppose you change the definition of what you call the bra.
Yeah.
Would that help?
Oh, thank you. Okay. So
That's what happens when in PT theories.
of course. Thank you so much. So I should have a note about that.
Okay, good.
Thank you so much. Thank you. Well, there are too many problems, too many questions in my mind. So I'm still studying. There is a voice. Okay.
Any other question, any other comment? Uwe.
Yeah, hello, thank you very much for your talk. A few slides later, after this current slide, you just one more. I will say stop when it's appearing. I didn't want to interrupt you during your talk. Still a bit later.
Oh, yes, please.
On the next slides, just even later.
Later, all right.
Yes, yes, on this one.
Oh, sorry. This one.
I'm just wondering. You have here different dimensions. You have in this left one, you have a three-dimensional. On the right one, you have a four-dimensional metric.
Yes, you're right. So it is also very surprising, but in fact, it wouldn't be surprising because at the beginning in the eta1 operator, there is a suggestion done by me, so by hand. In this operator, I'm using the square root of sine phi. So if I take this square of sine phi out, so this metric tensor will be 3, of course, dimensional. I mean, not 4 by 4. So at this point, because I checked it, then it will be reducing this matrix operator, but it still includes the sine square theta L square sine h square of tau right here. So it will be the same with the previous one. By the way, there should be a mistake that I make in here, because the mistake is in fact the sign. Sorry, I have to fix the sign. This should be negative, positive, positive. Okay, so it is really surprising. So it's a kind of expansion of the metric tensor or the space. So I don't have any idea what does it mean in physics. I try to find the meaning, and I searched the literature and couldn't find anything about it.
So which dimension are you somehow canceling in this approach from 4 to 3-dimensional?
Yes, yes.
So it's just one of the radial dimensions in the end of the. So you're reducing your sphere just to an interval or something like this.
Yeah, maybe. So it's the kind of I think that it's like in the case of the Schwarzschild space-time, it can be a sort of expansion of the Duster metric tensor. Maybe it's the hyperspherical expansion. It may be corresponding to hyperspherical expansion, but physically, I don't know the meaning of it.
Yeah, I think what you may have is the induced metric.
Yes.
On the 3 space, where you treat the phi direction as the normal to the 3 space.
Yes.
Because then you can construct on the 3 surface, you can construct a Riemann tensor that doesn't depend on the 4th coordinate.
Oh, yes.
Yeah, okay. Is this somewhere explained in your paper somewhere? This technique? I'm just wondering. I would just like to see the details of it.
Oh, yes, I remember. But unfortunately, I didn't give these references in here. But as far as I remember, there are some studies, but I still don't know the physical meaning.
No, I would just be interested in the technicalities.
Yes.
A little bit to see the details, how you're arriving there, and what
course.
is the trick to reduce it and what to extend it and so.
Of course.
Can you send me a
Of
reference?
course, sure.
Just like just for curiosity.
Of course, and that would be making me happier because at the end, this means that I can share my calculations and share the ideas with you. So thank you very much.
Okay, thank you. Okay,
Thank you. Thank you so much.
More questions, comments? If not, then let's thank Özlem again. Thank you very much.
Thank you so much.
Thank you.
I would like to thank you to all and for your joining. And I think on Sunday there is Easter. So happy Easter to you all.
Okay.
Same to you.
Take care of you.
Thank you very much.
Can you send us your slides as well, please?
Of course, I can say.
Okay.
Of course. So good afternoon there. So good evening for me. Okay, thank you so much.